Recirculation is practiced in stone filters for the following reasons. First is to increase contact efficiency by bringing the waste into contact more than once with active biological material. Second is to dampen variations in loading over a 24-hour period. The strength of the recirculated flow lags behind that of the incoming wastewater. Third is to raise the dissolved oxygen of the influent. Fourth is to improve the distribution over the surface. And fifth, to prevent the biological slimes from drying out and dying. Because the more dilute the incoming wastewater, the less likely it is the recirculation will improve the efficiency. So the second stage of trickling filter acts as a polishing step for the effluent from the primary stage by providing additional contact time between the waste and the microorganism. Next, we have the oxidation ponds. It is a pond that receives partially treated wastewater. Sewage lagoon is an example of the oxidation ponds, a pond that received the raw wastewater. Classification of ponds. Aerobic ponds. This is a shallow pond, less than 1 meter in depth, where dissolved oxygen is maintained throughout the entire depth. Next, we have the facultative ponds, 1 to 2.5 meters deep, have an anaerobic lower zone, a facultative middle zone, and anaerobic upper zone maintained by photosynthesis, surface aeration. So if this zone maintain photosynthesis, there's a light that can still pass through within the zone. Anaerobic ponds, from the word itself, anaerobic, wala ng air. Deep ponds that receive high organic loading such as the anaerobic condition prevail throughout the entire pond depth. Fourth is the maturation or tertiary ponds or the polishing ponds. These are ponds used for polishing effluents from other biological processes. Fifth, we have the aerated lagoons. Aerated means there's an introduction of air to the lagoons. These ponds oxygenated through the action of surface or diffuse air aeration. A secondary clarifier is important because high solid loading and fluffy nature of the activated sludge biological flock, and highly desirable that sludge recycle be well thickened. In secondary clarifier, the effluent is more clearer and also cleaner than from the primary clarifier. The primary clarifier has a type 2 settling. This secondary clarifier characterized type 3 settling, which accomplish both clarification and thickening of the solids. For the secondary clarifier has an overflow rate of 16 to 30 meters per day for average flow in a conventional process. The solids loading rates ranging from 100 kilograms to 150 kilograms. Capacity less than 3,800 cubic meter per day should not have hydraulic loading greater than 250 cubic meter per day meter of weir length at peak hourly flow. Plants larger than 3,800 cubic meter per day, the weir loading rate is specified as less than 350 cubic per day meter. In designing the settling basin, we have the minimum and the recommended depth for each diameter. So we have, if the diameter or the tank diameter in meters is less than 12, the minimum depth is 3 meters, but it is recommended to be 3.4 meters. If the tank diameter ranges from 12 meters to 20 meters, the minimum is 3.4 and it is recommended meter is 3.7. If the tank diameter is 20 meters to 30 meters, the minimum is 3.7 and the recommended is 4.0 meters. If the tank diameter is 30 meters to 42 meters, the minimum side water depth is 4 meters and the recommended is 4.3 meters. And if it is the tank diameter is greater than 42, the side water depth in meters has minimum 4.3, and it is recommended to be 4.6 meters. Clarification and thickening of the biological solids is desired in secondary clarifier. So, the secondary clarifier design protocol requires the calculation of the surface area or plan area of the clarifier based on the clarification and thickening considerations. The secondary settling basins are normally rectangular or circular with the 5 feet or 1.6 meters intervals in plan view. Secondary clarifier design for attached growth systems. It is similar to primary clarification. The main objective is clarification of the wastewater and not the thickening. The sludge that is collected in this clarifier is often pumped back to primary clarifiers for concentrations with the primary sludge, and otherwise it is removed from the secondary clarifier and pumped directly to sludge processing facilities. Disinfection of wastewater. It is very important to disinfect our water, especially the wastewater, because of the different pathogens and viruses that are present in the wastewater. Addition of chlorine gas or some other form of chlorine is the process most commonly used for the wastewater disinfection in the United States. Wastewater flows into the basin and held for about 15 minutes to allow the chlorine to react with the pathogens that are present in our wastewater. Same with the disinfectants or chemical agents used in disinfecting our drinking water. We have also here for the disinfection of the wastewater are the chlorine dioxide, chloramines, sodium hypochlorite, calcium hypochlorite, and ozone. This ozone is not usually used because there's no residual formed, and the half-life for this is 20 to 30 minutes. The sodium hypochlorite is the most used in disinfecting the wastewater.